The metals versus acids lab. We will be reacting several metals with several acids. If these are good acids, it's going to be this one, and this one. If these are good little acids, well, they should do exactly what they're supposed to do. And what are they supposed to do? Well, they're supposed to react with metals, aren't they? Well, at least if a metal is not those, above hydrogen, all of those should react with an acid. Ooh, all the ones above hydrogen, but not necessarily those ones down there. Well, maybe we have one of those so-called noble metals in here, but otherwise we would expect to get a reaction with a metal. That's what acids are supposed to do. Well, you know what? Really, they don't. Really, what acids do, all they really do is they fall apart. What's that word? The D word? Dissociate. Dissociation is when an acid breaks apart. Here's an example with hydrochloric. It's funny how I'm always using hydrochloric as my example, isn't it? Well, dissociation is when the proton or the hydrogen ion is ripped off. It donates it, but it's really being ripped off by the surrounding water molecules, and that's what makes the hydronium. And every acid has hydrogen that can come off and can generate hydronium. And then once you generate hydronium, well, that's what does all the work that acids get credit for. That's really what reacts with the base metals, most of the metals. So, in a way, as Yoda says here, an acid's very weakness becomes its strength. Because if it easily breaks apart, it generates more hydronium, and then the more hydronium you have, the more reaction, the stronger the acid is. So dissociation is a major thing when understanding acids. The more an acid dissociates, the more hydronium is generated. Okay? And then, of course, we have a scale for measuring that. The pH scale that measures the concentration of hydronium or hydrogen ions in a solution, the power of hydrogen. And, well, these are all acids. So what color do we expect it to turn when we put in the drops of universal indicator? Well, certainly not purple, not blue, not even green. That would be distilled water because bases are purple and blue. Distilled water is green. Yellow would be a pretty weak acid. And then, or pretty low concentration, let's say. And then if you get to orange and red, that's what we expect. We expect colors like orange and red. So if we see orange and red, that's no surprise. But if those colors are to disappear in any of the reaction, then that means there's no more acid left. So keep that in mind. Pay attention to the colors that come after the reaction is done. Okay. Also, acids are supposed to be electrolytes. So we can check that with the conductivity indicator. We can check if they're electrolytes. And then all of these reactions, well, you know what? Some of them might not even react. So we'll check if there's a reaction, looking for the signs of a chemical reaction, change of color, evolution of a gas, an odor that's given off. You won't be able to tell that on the video, but maybe it'll be mentioned by my little assistant, by my big assistant, I should say. And also change of temperature is a good one. Well, that's why we're measuring it with a digital thermometer for the thermodynamics. Remember that if it's an endothermic reaction, heat is absorbed by the system. So generally, the temperature on the thermometer will get colder. If it's an exothermic reaction, heat is released from the system. So generally, we expect the temperature on the thermometer to go up. Right now, 23.0 degrees Celsius. That's probably the temperature of all of these that have just been sitting here for a while now. So if the temperature goes down, it's endothermic. If it goes up, it's exothermic. That is a very simplistic version of thermodynamics, but it will suffice for this lab. The instructions for the lab are written for a well plate, but so that this can be seen on a camera, we are going to do it in beakers instead. So instead of well plates, these guys, instead of the well plates, we're going to be using beakers, but it's the same reactions. You would record them in the same location on your lab, the same spots. So what did you see here? Was there a reaction? Strong with bubbles, weak with bubbles, slow reaction, no reaction, color, anything. Record it very small in these boxes. Okay, and then you'll be able to see, and if there's no reaction, well, make sure to record that too. Don't just leave it blank. Just say nothing. However, you got to wait at least 5 minutes before you decide that. Okay? So the acids we're using are hydrochloric, sulfuric, and acetic. Now, all of these can actually be harmful, so we got to wear safety goggles. Humphrey Davy forgot this once. This is one reason that we always wear our safety goggles. Great chemist, by the way. And the acids that we are not using in this lab, or wait, maybe we will. Oh yeah, why is this little lemon here? That is concentrated lemon juice. Well, that is citric acid. That is also one of the old acids that's been known of for a long time. It isn't the originator of acids, but it's been known about for a long time. And we're going to do a little experiment with the citric acid. Okay, and what about carbonic acid? Oh yeah, carbonic acid. I love Pellegrino. In fact, any carbonated beverage is infused with carbonic acid. That's an acid, right? So let's try carbonic acid on some things. What about nitric acid? Well, nitric acid we do not use indoors because it produces lots of hazardous pollutants. So that one you've already seen in some demos, but we're not going to be using it today. And we are going to be looking at the archetype of an acid and the epitome of an acid. These are two vocabulary words you should know. Just in general, you should know them, but in this case, we're going to use them. So what's the archetype? The archetype is the originator for a type. So what is the archetype for acids? The OG acid, the original acid. Well, that is acetic acid. The name acetic acid comes from the Latin word vinum acetum, which means sour wine. We call it in English vinegar, which means sour wine also. So acetic acid was the first known acid, and it was the originator. The problem is it's a little complicated there. All that going on, it's kind of hard to understand. So instead of trying to understand something from its archetype, we often rely on its epitome. The epitome is the best example of its type. For example, she was the very epitome of a great student. Okay? That means the best example you can think of. So what's the epitome of an acid? Boom! Hydrochloric acid. Have you noticed? I've been using that as my example over and over and over and over because it's so simple. It's easy to understand. It's a good little acid. Okay? And, well, those are all acids, but what about antacids? What's the best antacid? Well, the best antacid is formic acid. Ba-dum-bum. Formic acid is what you get if you take an ant and squish. It's what comes out. It's an acid found in ants, like maybe not Ant-Man, but those little guys. So formic acid, anyway, I probably shouldn't end on a bad joke. So that is the metals versus acids lab. Bum, bum, bum. The metals versus acids lab. Kind of a quick lab, and I'm not going to perform it. My big assistant is going to perform it. Say hi, Giovanna. Hi. Okay, so she is going to react a bunch of metals with a bunch of acids. So first of all, Giovanna, could you put the metals in? Yeah. Could you say the name of the metal you're putting in? Do you want help? Sure. First one is Al, my Uncle Al, aluminum. The thermite is his nickname. Well, I mean, he's involved in the thermite reaction. So she's putting in a little scoop of in each one. Okay, that's the Al. The next one is, do you know what that one stands for?
Copper.
Copper, good. Cu, cupros, or cuprum. It's from the island of Cyprus, is where they used to excavate it in the ancient world. I'm going to come on this side to see better. So we've got aluminum in the first column. We've got copper in the second column. And do you know what the next one is?
Zinc.
Zinc, good. There's this old 1950s chemistry video called The Importance of Zinc, and I've always been trying to find that. It's so hilarious. It's like all the things that we use zinc for, you would never know, Giovanni, you'd never know it. Like pennies. People think pennies are copper, but they're... Okay. Let's not get started about quarters. Okay, so what are you putting in now? The last one is? Mg? Magnesium. Because it comes from magnesia grease, just like magnets do. Did you know that? Magnets are named after magnesia grease, and so is manganese, but we're not using manganese. We're not using manganese. I shouldn't have mentioned it. So now she's put in all the metals. So what do you think the next thing is going to be?
Universal indicator.
Oh, yeah. Bam. Good. She's going to add universal indicator to what?
To the metal.
Each of the... Those are the acids.
Yeah.
She's going to add universal indicator to the acids. So what color do we expect it to turn? What color would you expect if they're acids?
I don't know.
They're acids, look.
Like red or...
Okay, let's add it. She's going to try to add equal numbers of drops. And you might have to stir it up with a pipette also. Let's add, oh, I think there was an extra drop in that one, so go ahead and add it to those. And then stir it up with the pipettes in each one.
Yeah.
Those pipettes have to stay in the same beaker to avoid cross-contamination. And kind of as we expected, they're all either red or orange. So now she is going to cross them all. Good, putting the cap back on, excellent. She's going to put in enough to cover maybe like 4 squirts, quick squirts. Each squirt is about 2 milliliters, so maybe we're putting in about 8 milliliters or so in each beaker. Then we want to watch for signs of a chemical reaction. You reminded me about the universal indicator, thank you. One thing I forgot though was to measure the temperature before the reaction, but do you know what? Look, here's our thermometer, it's been sitting here, 23.1. These have been sitting here. So they're probably the exact same temperature according to thermodynamics. Okay, temperatures equalize. So which one was the more dramatic of this particular row? Which metal?
The zinc.
Okay. Now keep in mind in chemistry, not everything starts immediately, so don't assume because something did not start immediately that it won't react. Maybe not all of these will react, but we can see some really good, how would you describe this? How would you describe what's going on here?
There's a lot of like...
Gas?
Yeah.
Do you know what that gas is?
What?
It's a dog. That gas is our dog in chemistry because it barks. You don't know what I mean? What's the most abundant element in the universe?
What? Oh no.
That's what this gas is. Hydrogen. Hydrogen. A lot of, when you react metals and acids, the hydrogen from the acid is given off. Well, that's quite a good one. Wow. Oh man. Oh. Whoa. It took a while to start. But then it went kind of overboard. Wow. And then what about this one? Anything happening there?
Not yet.
Okay.
This one's, I'm like,
That's okay. That's
I feel
okay.
like it's gonna like...
Yeah. I'll make new placards. That's just for the dramatic effect. Okay, now what acid are you putting in now? H2SO4?
I don't know.
What is H2SO4? Sulfuric acid. She's putting in the sulfuric acid now. The first one you just saw was hydrochloric. Ooh. Can you mention anything about the smell or the odor?
It's like tingly I guess. Like, I don't know.
Do you know how I would describe it?
No.
Nasty. It's not good.
I'm like just now expecting something to just like I don't know.
We've got all the ventilation going, so this is not going to be confined. Did you know what hydrogen does in the presence of oxygen in a spark?
Oh, wait.
Did you ever hear of the Hindenburg?
What?
Ever hear of the Hindenburg disaster?
No.
Oh, good.
Okay.
No, it's kind of hard to confine hydrogen. When hydrogen is produced, it very quickly will react with the oxygen and make water in the air. Wow, so that reaction took a while to get started, but look at that. Cool.
Well, it's kind of like hot.
So now what do you see going on here? How would you describe these?
Oh, wait 1 second.
Which one started the fastest this time?
This one.
Which one is it?
That's the magnesium.
The magnesium started the fastest? Okay, what about the zinc? Didn't the zinc start quickly last time?
Yeah, not this
Is the
one.
zinc going?
Oh, a little bit.
A little bit going?
I'm just gonna step
Do you see
back
any
after
more
I do
red
this.
color in these? Any more red color left?
Oh.
Where's the magnesium? Look, where's the magnesium?
Oh yeah.
There's that nasty smell.
Yeah. That one is just yeah.
But remember that we want to keep an eye on these guys because chemical reactions don't always start right away. You want to give them some time to react. Okay, so what's the next one, Giovanna? What's this one? What's this one? That is acetic acid.
Okay.
Acetic acid. So now she's putting in the acetic.
Oh my god. I don't know how this is
Acetic.
gonna react.
Acetic sounds like the word acid, right? And that's not a coincidence because the word acid and the word acetic came from the same root, which means sour. Think of a lemon, right?
Mm-hmm.
Sour like a lemon. So we're not going to taste these because imagine what these would do to our tongues.
I don't want.
We don't ever taste lab materials, but if you did, you know they would be sour.
So far, the copper
Before your
hasn't
tongue-
done anything. Like in any
Copper
of them.
hasn't done anything in any of them? Interesting.
Just sitting there.
Good observation. So let's see if it takes a while to start or if it just is a non-starter. as
Oh
they
my
say.
god, I can still smell it.
Which one do you think you're smelling?
This one and this one.
Okay, keep going. Okay. So she put the acetic into the zinc, and now she's putting the acetic into, she's about to put the acetic into the magnesium. And then we're going to be done with the regular,
Oh my gosh, this one's gonna.
we're going to be done with our regular battery of reactions. Okay. Our 12
I'm
reactions
gonna
that
step
we're doing.
back after this one.
Yeah,
Okay.
you don't ever want to be right above. No, wait a second. You don't ever want to be right above these. I was going a little bit too high above them
Oh.
just to get the right shot, but I can actually move the camera.
Here we go.
So notice that metals have different amounts of what we call activity, how quickly they react, and so do acids. So certain combinations react more than others. Now let's check the temperature. Oh, we didn't check temperatures. If it was 23 to start with, check the temperature of this one right now. Getting fogged up. What is
I
that?
can see it. It's like 985.
It's getting up close to 99.
Oh my god.
It's actually boiling the water. That's actually boiling off the water right there. That's how hot that reaction is.
Smells bad. Oh my god.
Yeah, so now go to this one. Well, acetate has a vinegar smell. Measure the temperature of these other ones.
Should I like?
Yeah, wipe it off in between. We should have gotten it while the reaction was full blown, but we should still be able to tell whether it went up or down by whatever temperature it is now. Okay. What is that one?
70.
70.1. Try the next one. Wipe it off. Good. Good technique. Next one. And remember, these might not be the maximum temperatures, but remember,
55.
make sure that you're not touching the glass. Lift it
It's
right
like
up.
it stayed around 55.
55. Okay. We should have gotten this one. Get this one over here.
I can smell it.
Now, we waited a long time for this one. So just remember that these all started around 23 degrees. These all started around 23 degrees. So this one, what would you say it is?
46.4.
Okay.
Oh,
And
there's
then
like a.
and then yeah, there's actually
You can
like a
look
big
down.
pocket in there. Interesting.
One second, I just need to wipe
Do you
all
want to break that open? Break that open with the thermometer,
Oh,
and you can
okay.
see what's under there. Like cut a little hole so we can see. Yeah, that it wasn't all filled up. Okay, that's good. So you can see that it was a big cavity. It was foamed up to the top.
Oh, it's sticking to the thermometer.
Okay, just get as much off as you can, and then let's get a few more temperatures. We didn't get the temperatures in this row, so let's get this temperature. And again, these are not the maximum, but
47.
it's going, yeah, 47, and it's going up. So all we really need to know is whether it went up or down. So,
Let's try
we
this
got
one.
that one. Let's try this
Oh,
one.
we did?
This one. What's that?
It's 39-ish.
I think
38.
38, okay. And then what's this one? This one right here.
Oh, yeah.
Remember to be slightly off the glass if possible. In the liquid, but off the glass is the best. Oh, this one didn't change much. It's going down into the 20s.
Oh, it's going down like 26.
26, a very little change in that one. Interesting. Okay, and notice the reaction didn't really do that much either. It's still even a little, notice the color, right? Notice the
Yeah.
color, okay.
Still
What about
smells bad.
these? Let's try these ones, the copper ones. Okay, so we're getting 25, 24. Oh, look, it's dropping down. 24, it's going back down. 24,
So I'd say
23. Look, so
Yeah, I'd say 24. It's like hovering right around there.
it's still dropping though. Hold on. So the funny thing about these is these might not have changed at all because it was 23 point.
Like they had no reaction. I mean, no visible reaction.
No visible reaction and maybe no reaction whatsoever. Okay,
Yeah.
try the next one.
I swear.
And is it similar?
Yeah.
Yeah, try the next one. Yeah, so maybe, just like it looks. Oh, this one, interesting.
25.
Okay, so there
25.
was, so that means there must have been something going on there, although
Maybe
it's
like a little bit.
not very visible. Okay, and then the only ones we didn't do, let's go through these one more time. Let's go
This
through
one
it.
too?
Yeah, let's do it again, just so we
I'm
get.
just gonna do this
okay,
one
this
first,
one
'cause
first.
It takes
Okay.
a while to get this to full. I'd say 24 or 23.
Oh, look, so that's the temperature we started at. Very close. So
Yeah.
not much going on in that one. What about this one?
23.
Yeah,
27.
interesting. So for these two, the temperature did not seem to
Okay,
change.
time for this one again.
Okay, and for these two, that one changed a little. So that's evidence of a chemical reaction, is a change of
I'm
temperature.
trying to get like a one spot where it's not
Is there any
touching.
liquid left in there?
No, it's
oh,
all
that might be the
crusted.
problem, yeah. But definitely it's,
Yeah, I can
well,
feel it
it
poking
may have
down.
been much warmer before, but it's definitely
Still
going up.
Yeah, 28.
Okay, that's fine.
Yeah, it's just like
All right,
poking.
so now as a bonus feature, so now what we're going to do is a reaction with some other acids. These are like bonus ones. We're going to use citric acid, like lemon juice, and carbonic acid, like Pellegrino. And could we use, let's just use two of the metals. Let's just use the zinc and magnesium, and we're going to just carry them down and put them right here. Go ahead and put the metals in. Same way. You can pick up the whole beaker, yeah. So let's just put the zinc in these two. Yeah, whatever, that's fine.
Oh my god.
As long as you get some of the small pieces, that's fine. And then the magnesium. It's a good scoop, the same amount
This
you
one
did.
had the most reactions than the previous ones. So.
Hey, don't give away the answers.
Oh.
Well, actually, the questions mostly ask about the acids, but another thing students can answer is which metal
Yeah,
react the most. Even though the questions on the lab ask about the acids, you could also talk about which metal had the most reactions. Okay, so now the lemon juice, this is concentrated lemon juice.
How many squirts is it?
Just squirt it in, squeeze it until it fills up to like about that level.
Oh, okay.
About something like 8 milliliters. Just squeeze it really hard. Squeeze it really hard. And then also in that one. Okay, and then the Pellegrino. Pellegrino, do we see any reactions happening?
Oh, this one is, and that one just, it's a little, it got murky.
Okay, Pellegrino,
I don't know,
just
but-
pour in a little bit,
Okay.
about the same amount, so it's about the same level. It might splash a little, that's okay. Okay, oh, and by the way, don't we want to see if they're acids? Are they really acids? Put some universal indicator in there. Maybe in this case, just a drop in each one.
Okay, I'll try to get it exact.
You know, it doesn't have to be exact. Is it an acid? Is it an acid? Maybe put another drop in. It's not very visible. Another drop in this one. Another drop in those two also.
Yep.
Okay.
That one's just frothing up, so you can't really get
And
it
then
down. That one I can't really tell because it's just the foam just...
interesting, but isn't that some kind of reaction is going on?
Yeah.
Well, see the red? That shows that right there, that spot is an acid. One thing we could do is you could try to stir it around with this end of the spoon, with that end.
Yeah.
Try to stir it around in there and see if it turns red. So is lemon juice an acid?
Yeah.
Yeah. And is Pellegrino an acid? Is it reacting?
Yes.
Okay, why don't we get temperatures on these? Temperatures on these reactions. 23.4 is the temperature right now. So let's see. The only problem is the Pellegrino actually might have been cold. So let's see. That could affect it. Let's...
21. Yeah, 21.
Interesting. Now remember, some reactions
And after
change
this
the temperature the other way.
20. What was that? 28.2. No, 29. 30.
Interesting. Oh, one thing I might mention is
Going
that
up.
this lemon juice was earlier in the refrigerator, so that could account for a lower temperature. I should mention that. So just keep that. We should have taken the temperature before and after.
21.
And the Pellegrino was definitely cold. So let's just get the other one.
21.
21, and what's the other one? Let's see which one is warmer of the two.
This is 20.8.
So which one was warmer of these two?
This one.
So since we didn't have an... Oh, you know what we can do? We'll ruin this Pellegrino. Let's get the initial temperature. Stick it right in there. We won't drink it. Just get the temperature. I wonder what the Pellegrino started at. What did it start at?
20?
Do you see what's on there? Do you see what's on there?
Yeah, 19.6.
Okay, so if it started at 19.6, and then we got those other temperatures that it changed to, and then what about the lemon juice? Let's just pour some lemon juice to get its temperature. Let's just pour some lemon juice into an empty, that way we know what temperature it started at, about this temperature. Now keep it off the bottom slightly. And so the lemon juice initially was 20.6. Okay, so it started at 20.6, and then we have the temperatures it changed to. And you can tell by that if it's endothermic or exothermic. And so let me go around here. And thank you, Giovanna. That was a great experiment. And could you please point out one last thing? Which of them you think there were no reactions at all in?
Okay, I would say these four.
Those four had no reaction whatsoever.
Yeah, the temperature didn't even change those.
Okay, that's a good sign.
This one went up slightly, and I think the most visible reaction was this one.
Yeah, but isn't it funny that didn't that take a little while to start?
Yeah.
So that's why in chemistry we have to be patient. And what else? What other reactions did you see?
This one just, and now everything disappeared from it.
And which one gave off the worst smell, do you think?
These two.
These point very clearly. I'm not sure which ones you mean. Those
And the magnesium one. The first, oh my god.
for the hydrochloric for the top row.
Yeah, they also
Okay.
had the biggest reaction.
Okay, well thank you. Wave bye-bye.
Bye.
And now with nitric acid. I'm going to do the same ones with nitric acid that we did in the earlier lab. Okay, so let's bring it closer. Let me get my squirts. 1, 2, 3, 4. 1, 2, 3, 4. Over. That's a good reaction. Whoa. 2, 3, 4. 1, 2, 3, 4. Remove this. We see a pretty vigorous reaction. 1, 2. Some of them might take a little while to start. Just keep that in mind. So got a little bit left over. I'm going to put some more in there. Oh, I just didn't have enough. That was part of it. Wow. That's interesting. And then what did we not get? Look at that jumping around. And we didn't get much of a reaction with the aluminum, but I have a little bit more aluminum. Little slices of aluminum foil I'm going to add. So it didn't react with the powdered aluminum much, so let's pour in some aluminum foil, slices of aluminum foil. And I've got a little bit extra nitric, so I want to sort of get rid of it before I neutralize it. And I'll pour that in there. You never want to leave nitric acid lying around, so I want to sort of neutralize all of this. It can do a lot of nasty things. It does things that no other acid does. Now, what about universal indicator? Have we neutralized the acid? Well, we can check by looking for how the universal indicator changes the color. I don't think we've neutralized that one. It's hard to tell with the blue compound. I don't think we've neutralized any of these. Well, it's really hard to tell. It's hard to tell with the chromium. This was the chromium one. It's hard to tell with the iron one because it already has that color, but it still looks like the acid is not neutralized. The acid does not appear to be neutralized. So we still see a little bit going on here. Oh, this reaction finally seems to be getting going. It could be because the aluminum had an oxide layer around it. It might have taken this long to break through that oxide layer. So maybe even though aluminum is pretty high up on the activity series, it's really just a little bit below, it's really just below magnesium. It's actually above iron and even above zinc. Okay, so maybe it's taking this long to get going. There we go. Finally, let me get my other camera ready. So it took a while for the aluminum to get started, probably because it had an oxide layer around it. But now that it's going pretty well. It started way after the other reactions had pretty much stopped. And the only thing that might have affected it is I did put in a few drops of universal indicator, and nitric acid is one of the acids that reacts with universal indicator. That could have been the trigger reaction that led to this reaction. Okay, so I'm trying to stay out of the fumes of this. But this is a pretty good reaction, so it did wind up reacting with the aluminum, just not immediately. Oh, there we go. Gotta stay out of these fumes. It's a very good reaction now. Very vigorous, as you'd expect from the activity series. If you look at where aluminum is on the activity series, you would expect a good reaction like this, but it just took a while to get started because of the oxide layers. Some of the others appeared to have oxide layers, but that didn't slow it down as much. It appeared that some of the magnesium ribbon had an oxide layer on it as well, because of course metals also. And see how the universal indicator has reacted. Does it look red anymore? No, because nitric acid actually reacts with universal indicator. Okay, so now I'm going to neutralize what is left. Watch this. and neutralize the remaining acid. Taking care of a very dangerous chemical with a very safe chemical. Baking soda.